Hey folks, it's Dr. Gilchrist. As you can kind of see, I'm hitting the wrong key. As you can kind of see, I'm here in my rugby shirt, which you just saw me from class today. So as you can imagine, I do not actually have a video for this one. And so it turns out that maybe the last few seconds or the last few slides of visual imagery, I do have something that I recorded last semester, but for this one, I do not. So I'm going to go ahead and go through this. Hopefully, this will not take more than 20 minutes of your time. So today, we are going to talk about objects and basically how we use our visual perception to act upon objects in the world. So we're basically going to talk about a couple of things. We're going to talk about Gibson's theory of direct perception, and we're going to talk about his concept of affordances. We're going to talk about something called time to contact, and then we'll finish by talking about Glover's planning and control model. Now, I will kind of mention we're not really going to test too much on Glover's planning and control model, but I will mention that your book, particularly around page 69, talks about the two visual streams that we have, our what and our where pathway. Um, Milner and Goodale actually talk a little bit about having what we call a vision for perception system and what we call a vision for action system. So vision for perception is all about using vision to recognize what objects are, which is analogous to that ventral stream. When we're talking about our dorsal stream, that's often referred to as our vision for action system. So actually figuring out where objects are located so that we have a better idea of how to interact with them. So I would take a look at page 69, 70 in your textbook to really get a feel for those two different models. We're going to start by talking about Gibson's theory of direct perception. So, what is the goal of visual perception? And one of the things that you may not appreciate is that up until maybe about 30 to 40 years ago, the goal of visual perception, if you ask most researchers what the goal of visual perception was, it would be to identify or recognize objects in the world, not necessarily to act upon them or interact with them, but to merely recognize them. Now, it's around 1980 or so that James Gibson really starts to gain traction by saying that the goal of perception is not just to identify or to recognize objects, but it's also about interacting with objects. There is a whole branch of research called embodied cognition, which is the idea that oftentimes the way that we think about the world is based on what we are doing with our bodies. That our body and our mind basically developed these processes so that we could use our bodies to interact with objects in the world. And in McRaney, this embodied cognition actually comes into play because we often talk about different things around us or different experiences that we have in body based terms. We talk about somebody being soft hearted or having a warm or a cold personality. So again, the way that we tend to think about things and these mental processes in basically people believe that these exist so that our bodies can interact with the world. Gibson is one of the main people that really talked about this with his direct theory of perception. So, what is involved in his theory of perception? So, basically, you are getting a wide variety of information through light patterns that are basically on your retina. So, you are picking up information through ambient arrays of light in this particular instance. And this is what Gibson referred to as an optic array. This is basically a simple structural pattern of light that is falling on your retina. Now, the optic array is going to provide invariant information. That means it won't change about your layout. This will include texture gradient, which we've already kind of talked about, and two things that we have not talked about, optic flow and affordances. So let's talk a little bit about optic flow. So optic flow is something that can only really happen when you're moving through the environment. And I would be remiss if I didn't mention that Gibson did a lot of work in World War II, basically helping train pilots to navigate and fly with aircraft. And so, what a surprise that optic flow and this understanding of optic flow is often presented as if an airplane is about to land on a runway. So, as you are moving through the visual field, you have a couple of different points that are going on here. So, in particular, the center of this visual field, which you are heading towards, is motionless. As long as you don't change direction suddenly, that central point that you are heading towards is always going to stay motionless. This is what is referred to as the focus of expansion. Now that stays motionless, but the rest of the visual field moves away and radiates outward from that focus of expansion. So this helps you figure out in which direction you are heading. Additionally, the speed with which that focus of the speed with which things radiate out from the focus of expansion helps you gauge how fast you're going. The farther away something is from the focus of expansion, the faster it appears to move. So how do we account for object recognition in perception? Gibson has largely said that some of these invariant properties include texture gradient, optic flow, which we just covered, and then the potential uses of an object, which he termed affordances. So just by looking at an object, you will directly obtain the potential uses of the object just from perceiving them. So for an example, just by looking at a chair, you know that it has an affordance of being able to sit in it. So one of the things that we will find is that most objects have multiple affordances. The one that you pick is often based on your mental state at the time. So for example, if you're really angry, a brick could be used to hurl at somebody's window or to use as a self-defense weapon. If you are interested in building shelter for yourself, you might perceive the affordance that a brick will allow you to build a house. With a book could be an affordance for reading or a doorstop or for killing a bug, depending on your mental state. And then Diet Mountain Dew is often going to have the affordance of being Dr. G's major source of fuel. So all of those are directly perceivable just by looking at an object, and objects will typically have more than one affordance. Is there actually evidence for affordances? Back in 2008, Pappas and Mack actually did show that this is in fact the case. Participants were shown images of objects, but they were often too fast to be consciously reported as being seen. And what's interesting is that the most common affordance primed motor activity in that respective area. So for example, if I look at a pair of scissors, scissors will afford cutting, and that's largely done by the hands. So if I briefly flash scissors, we would see primed motor activity in the area that represents the hands and the fingers. So this is some potential evidence that affordances are directly perceived. Wilf and colleagues back in 2013 actually found that motor reaction time was faster, being able to act upon an object was faster for objects that actually can be grasped versus those that can't. So there's some potential evidence for the uses of an object being directly perceivable as soon as we look at them. So I want to talk a little bit more about Gibson's theory, because Gibson's theory is not just about interacting with objects, it's about moving through our environment. And Gibson believed that this happened with something called global radial flow. So I mentioned before that focus expansion helps you get a pretty good idea in which direction you're moving. Everything radiates out from that motionless focus. So we end up aligning the focus of expansion and optic flow with our goal. So if we know there's a certain direction that we need to head in, we're going to make sure that our focus our focus of expansion aligns with the direction that we need to go, and that the optic flow in the environment matches with this. And this is what is referred to as heading. So if my optic flow is located in this direction, but my goal is this way, I need to turn my head to make sure that that focus of expansion and optic flow is aligned with where I want to be. But what if you can't move directly to the goal? So oftentimes with driving, I need to be on an area where there's road. My car doesn't have the capacity nor the ability to go off road. It's a tiny little hatchback. So if I can't move directly to the goal, what should I do instead? In this case, we can use our eye movements and our head movements to help us. And if a path curves, it's going to get even more complicated. Heading is a lot less helpful when the road has to curve. And in this case, because your focus of expansion is going to have to change. And in this case, for you to be able to do this, you will need to start identifying future points in your path. And most of the time, those aren't going to be right in front of you. They are going to be some distance away. So in 2008, Wilkie and colleagues actually looked at heading and future points for curves by having people ride on a bicycle simulator and ride through slalom gates. Now at slalom gates, what you have to do is you constantly have to curve back and forth between pairs of gates. And what they found when they looked at eye tracking is that people are in fact doing future points as the slalom path curves. Participants will focus on the current gate, but then just prior to entering that gate, they will immediately advance their gaze to the next one so that they can move towards that gate more easily without a lot of difficulty. So now we're going to talk about time to contact. That's pretty much it for Gibson's direct theory of perception. So now we're going to talk about what happens when an object is coming right at you. And this can be particularly scary. The longer that you look at this picture, I hope you can kind of see what's wrong. This poor person ended up taking a bat to the face because of objects coming at them. So how do we figure out how quickly a ball, let's hope it's not a bat, but a ball is coming towards us? In this case, we're going to use the equations of physics. We can estimate, now if we're using physics, figuring out whether an object is near us or not is actually pretty simple. We can estimate based on how far away the object is from us and judging how fast the object is going, right? Basically time so distance equals rate times time. So we should be able to figure out the distance and the rate of speed to be able to figure out how much time we have before this ball hits us in the face and hits my computer. But the thing is, that's really hard for us to do. We don't always have time to figure out how quickly an object is going to make contact with us. So what we're going to do instead is do something called tau. So time to contact is based on how quickly an object will reach our eyes, and we use tau as a way to basically figure out how quickly that will reach us. Now, tau has some of the basic ideas of how to figure out time to contact using physics, but it's done so in a bit of a cruder way. So we basically figure out the size of our object's retinal image. In this case, that's going to be kind of our judge of distance, looking at the retinal image and its size. And then we're going to look at rate and divide by rate to get time by looking at how quickly it expands on our retina. The closer that an object is to you, the bigger it's going to be on your retina. So the more quickly that it expands on your retina, the more quickly its rate of speed. So we're basically taking some very crude metrics of physics to help us. We're going to look at the retinal image and divide it by the rate of its expansion. Now we are going to assume a constant velocity. So this means that no sudden accelerations or decelerations are going to help us here. What's going to happen is that if we get a sudden acceleration, we are going to overestimate the time to contact. If we are having a sudden deceleration, we are going to underestimate our time to contact. Now, there are some problems with tau. As I've kind of mentioned, objects can accelerate. Generally, tau is based on time to contact with our eyes, so this won't necessarily work with something like a car, where we're basing it on time to contact with our front bumper. Additionally, tau is only going to work on symmetrical spheres. It will not work on things like footballs. It will not work on things like hockey pucks or baseball bats. It can only focus on symmetrical spheres. Now, despite those limited circumstances, can tau work? And it turns out that it absolutely can. So, one of the ways that people have done this is by changing the rate of expansion by basically having people catch very rapidly deflating balls. And what we find is that by the rate of expansion basically slowing down, people will use tau to have later grasp. So they're able to appropriately calculate tau even as that rate of expansion changes. Now, we do use some other things for time to contact besides tau. We can use familiar size, and I think this is probably where cars kind of come into play. We can judge when we're getting too close to a car based on how big it is on our retina at that point. And we know that generally, if this gets any bigger, it's going to be in our front bumper. So we're able to judge familiar size. We can also use binocular disparity to help us judge depth and distance. We're going to finish up by talking about the planning and control model. So, how do we actually use the visual system to act upon objects? Back in 2004, Glover proposed something called a planning control model, and he basically said that we have two different systems to do this. First, we have a planning system that is used before the movement, and this basically helps us select a target. It considers what kind of grasp we need to interact with it, as well as the timing of our movements. Now, this is going to be pretty slow. Making a plan can be slow. You're taking into account a lot of information. You are having to process this very consciously, and it takes some work. Then we have the control system. The control system executes the movement, and its goal is to be fast and accurate. So this is going to ensure accuracy of movements. This is going to be based on both visual feedback, so how close we're getting to grasping an object, as well as our bodily feedback. Now, this is really important. This is influenced by the object's spatial properties, not the context with which they are surrounded by. This is generally going to be very fast and not conscious. And interestingly enough, Glover and others have found that the planning control model actually has some distinct areas in the brain. So we have our planning model, which by and large is in the occipital lobes, as well as parts of the parietal lobe, looking a lot like our dorsal system, aka our wear pathway or our vision for action system, or our planning system rather. Our control system is largely going to take place in other parietal regions, as well as some motor regions and the cerebellum. Now, this has some really important implications based on what we've learned. Because the control system is designed for accuracy, it's fast, and it's not conscious, that means if you make mistakes interacting with something, it wasn't because of the control system, it was because of the planning system. So interestingly enough, your book, and I would say take a look at this, your book mentions that illusions tend to happen because of the vision for perception system. The vision for perception system, aka your ventral stream, is largely developed for recognizing objects. So you're going to be more likely to fall for illusions when you are relying on that system. What researchers have found is that when you use the wear pathway, the vision for action system, if you make illusions things that are touchable, that you can interact with, the illusions generally fail. Now, the illusions happen in the planning control system because similar to the vision for perception system, it's largely due to context. The planning system is what takes into account context. The control system does not. So this is another case where if you were able to interact with the illusion, you would not fall for the illusion. So this is pretty similar to Milner and Goodale's system, where the ventral stream is vision for perception, and this is where illusions tend to happen, versus the dorsal ware pathway vision for action system. But the Glover system focuses more on how processing changes rather than vision for perception versus vision for action. Now, is there evidence for these systems? Um, Glover and Dixon actually did a really cool study in 2002 where people had to reach for objects and they either had small or large written on the object. And what's interesting is that Glover and Dixon found that at least in the early reaches, people had a larger grip size for objects labeled large, even if those objects themselves were not large. And as you move closer to the object, the grip decreased to be more accurate. Additionally, if you apply transcranial magnetic stimulation to areas like the superior parietal lobe, which is a part of our planning system, what we do tend to find is that that disrupts the movement and we make more mistakes. Now, there are some additional issues with this system. The planning and the control systems do interact in very complex ways, and planning a movement involves more complex processes than Glover's model originally assumes. Additionally, this is largely focused on the body, but we also interact with objects in the world using our eyes. And it is interesting that there's more of a focus on body movements rather than eye movements here. So, folks, that's all I had. I will send you a link to this shortly, and I will see you on Sunday night for our review session. Bye.